So, this is a video about cheese and the letter, and that is going to raise a couple questions. First of all, what the fuck does this video have to do with cheese? And I'm going to answer that. And also, when I say the letter, what letter is it that I'm referring to and what's the context of all this? If you want answers to these questions, you're going to need to keep watching. This video is brought to you by Squarespace. More about them at the end of the video. So I'm going to start off with something that seems completely unrelated, but I swear everything connects. I want you to imagine a square of, let's say, side length 1. So you have a 1 by 1 square, and on that square, I want you to imagine that we just pick two randomly distributed points. They can be close together or they can be far apart, but the important thing is we are going to measure the distance between, these 2 points. So if they're close together, that distance is going to be close to 0. Whatever that may be, I want you to take that distance number and just tuck it away over to the side. Next, what we're going to do is we're going to pick 2 different points. Calculate that distance. That's probably going to be a different number, most likely. Take that, tuck it away to the side. And again, 2 more points, distance number, tuck it away. And we're just going to keep repeating this over and over and over again. And the question is, if you do this for infinitely many pairs of points, and really you kind of go through every possibility, every pair, what is the average distance going to be? And without thinking about it too hard, I know my first instinct when I heard this question is like, I don't know, but maybe it's going to be a half. Just kind of seems right. You have a 1 by 1 square. So on average, you have some big ones, you have some small ones. It averages to the, average between 0 and 1. It's going to be 0.5. Turns out this answer is wrong. One way to kind of see this is, what if you have 2 points at like the opposite corners? Well, that's going to have a distance of square root of 2. If you use the Pythagorean theorem, this is bigger than 1. So, maybe 0.5 is a bit small since you have possibilities for big distances. Then you also have all these pairs of tiny distances, and really, there's no easy way to calculate this. So what is the answer to that question? What is the average distance? Well, if you want to find out, keep watching. So the answer is this, which kind of seems like a random thing. There's a natural log in there, and it seems much more complicated than it should be. It turns out that pretty much the only way to solve this problem is you kind of use calculus, which is the way that you would approach this, regardless of whether or not you know what that means. You take some integrals, and this is the answer that you come to. It's a little bigger than 0.5, which kind of makes sense since you have the square root of 2 possibilities, but it kind of seems like a very complicated thing, and if you look at how people derive this, it just seems like I don't know how they approach that. And that gets much more complicated if the shape is not a square, which is something easy to work with. What if we had a circle and we looked at all pairs of points and we wanted the average distance, or even a triangle, or maybe a arbitrary shape? What if we actually looked at all the letters and said, what is the average distance for the letter A, B, C, D, E, F, and compared to all these letters, which one is going to have the biggest average distance? Which is kind of what this video is about. That's the question I wanted to answer. And before we actually answer this question, we need to kind of have a way to calculate this, because I don't know how to do the integrals. It's going to get much messier once the shape gets much more confusing, especially if it's a letter. So here's the technology we are going to use to answer the question. Well, if you think about it, what I basically said is sample a bunch of different distances. I mean, ideally you sample all of them, and there's infinitely many, but you sample a lot of them, and you calculate the average, which is going to converge the more distances that you take to hopefully something that is very close to the right number. Meaning, the way that we can answer this approximately, without like exact answers, is we literally sample more and more and more and more and more, and come up with an answer. So we can see that this thing works. We can actually get this number for a circle, a triangle, and here's actually what's going on behind the scenes. What I'm actually doing here is I'm taking my shape and I'm just distributing a bunch of points. Not infinitely many, but just a bunch of points, and then we have a node network that basically what it does is for each point, it's going to select a partner point. And we're going to calculate the distance for each of these, take the average, and it's a very close approximation. And since we now have a way to kind of on the fly calculate this distance number, which is what I'm going to be calling it from now on, for any shape, let's actually explore some properties of this distance number. First of all, if we take our original square, the 0.52 whatever, and make it bigger, of course our distance number is going to be bigger, not necessarily proportionally. In fact, it's not proportionally, which is kind of the weird thing about this, but in fact I just did some testing on this, and here's what I found. It's pretty interesting. If we take our square and scale it up uniformly, that is x and y changed together, it actually is proportional in a sense. So you have 0.52, the number we have before, make it a 2 by 2, now it's double that number, 3 by 3, triple that number, etc. So you might be inclined to say, oh, it's a proportional relationship, but really it's more of a square root relationship, because if you have a 2 by 2, you haven't doubled the area, you've made it 4 times bigger, and only then does it double the distance number. 3 by 3 means 9 times bigger, but the number triples. So it's kind of like this square root relationship. Back to the thing. We make this bigger, it's going to have more opportunities for big gaps in distance, and you can see how this changes. Interestingly, the way that you actually change this shape seems to matter. So if I take a square and stretch it on the x-axis, make it twice as big, the distance number does not get twice as big. It's not proportional. More interestingly, imagine our square is now made of cheese. Now we're getting into the cheese part of it. Basically made of a material that we can morph and cut and stretch and all this. Well, let's say that we take our square, we cut our cheese in half, and just take our chunks and move them off to the sides. You can see the distance number actually increases, even though we have not even changed the amount of material, we've just relocated it. Again, this is happening because now we have pairs of points that could exist on opposite islands. So the distance between these seems to matter, and you can do a whole bunch of different stuff with this. And it seems that the distance number, again, isn't directly proportional to area, but it also says something about the connectivity or how distributed our shape is. So, you know, if you separate it, things tend to happen. Another interesting thing I found when I was playing with this is if you take our shape, again, let's say the square, and you cut a hole from the middle, so we just take our cheese thing and just remove a circle from it, the distance number increases, even though, again, we have literally less material. We're removing it from the middle. Somehow less material makes for a bigger distance number. Again, this kind of makes sense intuitively without thinking about it too hard. You're gonna have a more likely opportunity to have pairs of points that are on opposite ends of kind of this ring that we're generating, but there's no reason that we can't cut a bunch of holes out of this, literally like cheese that, I don't know if I've ever seen cheese like that in the supermarket, but that's like the cartoon cheese I have in my head. We can cut out a bunch of different circles out of this and see what that distance number becomes. And so far, all I've really been doing is just showing you a bunch of examples saying, wow, this thing increases it or decreases it, and look at how the shape matters. I did some research to see if anybody actually formalized this, and I was like, distance number, anybody know what the fuck I'm talking about? And in my research, I actually only found a single paper that somebody wrote for this like measurement for convex shapes in 2 dimensions. So it seems like this is a thing that isn't like too thoroughly explored, but if you were to just ask for my opinion, and I don't really know what's going on, I would imagine that this distance number in some sense is not directly, but proportional to the variance of a surface. I want to know kind of how spread out this data is from the center, and my theory is the more variance, the more this thing is kind of like spread out from the center, the more distributed our shape is, the bigger the distance number is going to be, because they kind of seem like similar kinds of measurements in my mind. And now for the question that I posed in my head like a week ago and never coded it up until now. If we were to take all the letters of the alphabet, whether they be lowercase or uppercase or whatever for some set font, which of these is going to have the biggest distance number? Of course, like the letter A has that gap in the middle, and we know that removing material can actually increase the distance number. But something like the letter B has this tall, I wouldn't say tail, more of a neck that provides opportunity for more distribution of points. So before I do that, it doesn't really seem fair to do that directly, because body odor, B-O, these are 2 letters that if we were to take them and kind of overlap them on top of each other, you can see they have a very similar shape. They have the circular thing, but the B is basically, you know, with the neck sticking out of it. So I feel like clearly this would have a bigger distance number. Before I run this calculation, I just want to do a bit of a normalization step. I'm basically going to take our square from before and say, no matter what letter or shape we have, cram it inside the bounds of this. We're kind of normalizing for one factor that might change it, and now we're all on an even playing field. We're gonna scale the things, we're gonna calculate the distance number, and to be honest, at this point of recording, I don't know what the answer is, which is why I'm saying the letters because I don't know. So stick around for the rest of the video if you want to find out what that answer is. I mean, I don't know what it is, but first, a message from our sponsor, Squarespace. So this video is brought to you by Squarespace. If you haven't heard of them, they are a service that will let you make a website in no time flat. Pick an award-winning template, just a website that already looks good off the bat, and replace it with your content. You don't need to learn how to code, you don't need to learn any of this nonsense. Make a website faster than you can say make it pretty quickly using Squarespace. Some features that you might be interested in that Squarespace offers automatically with its service is analytics, so you can track how many people and who are going to your website. This is useful information, as well as email campaigns. So once you know who those people are, you can send a personalized or brand message to the people that are going to your website. And while you already get access to all of this with a very cheap monthly subscription, I am here to make the deal even sweeter. You can click my link in the description, really, it's there. Click it, and you can save 10% on your first purchase of a website or domain. So if you're making a website, make it with Squarespace. And now, the moment you've been waiting for, which letter has the biggest distance number? Let's find out. Okay, so I've crunched the numbers. This is the moment you've all been waiting for. Can I get I don't know if you can hear that. So with the font that I used, notice that this is going to be different for every font. The biggest distance number for capital letters is the letter Q. And for lowercase, it's the letter M. Again, this is going to be different for every font. But by the way, if you were to compare uppercase and lowercase and just put them all in one pool, highest distance number overall, capital Q. Yeah.